Let's have a look then at question 7. Okay, question 7 is a really interesting one because now they're giving you an expression to integrate, but they want a volume of revolution in question 7. So they give you this function that y equals x square root 1 plus x cubed, 1 plus x cubed, and the limits of integration for this are meant to be from x equals 0 to x equals 2, I think, yes, from x equals 2. And it's that bit in there, it's the bit that's inside the radical sign that is going to cause all the problems. This thing here is called a radical sign, in case you didn't know. The square root sign is a radical sign. So that's going to cause problems. So how about we try and make a substitution there? We're going to let u equal 1 plus x cubed, which means when x equals 0, u equals 1. When x equals 2, u equals 9. And du dx is equal to 3x squared. So du is equal to 3x squared dx. Crumbs, how does this all work out? Well, remember, it's a volume of revolution question. So I'm just going to take you back to the last exercise. For a volume of revolution, we're going to have an expression that looks like this, an integral from a to b, and it's going to be the function of x in here, all squared dx. Alright, in this case, if we looked at that, we would have that the volume is going to equal pi outside of, and the limits would have been from 0 to 2, outside of x times 1, oopsie daisies, 1 plus x cubed to the power of a half, all squared. So that's the function of x, all squared. There's the function of x, and it's all squared. The function of x, all squared. Maybe if I put it in square brackets, the correlation is a little bit clearer between the two expressions. There's the function of x, all squared, with respect to x dx. That's what we're aiming at. Let's just maybe get rid of this power here. It's not hard to get rid of that power because there's a multiplication sign there. Again, harking back to your index laws, from 0 to 2, that will be x squared outside of 1 plus x cubed, and a half times 2 is 1, so that just becomes that expression there. All right, I'm going to rearrange this. Pi from 0 to 2 of 1 plus x cubed, x squared dx. Now what I want is I want this whole bit here to look like that whole bit there. Those two things need to look the same. So I'm going to put a 3 in here, but I've just made that whole expression 3 times bigger than it originally was. So I put a 1/3 out the front, which brings it all back down to size again. This makes it bigger, this 3 makes it bigger, so I have to put that 1/3 there to bring it back down to its same numerical size. And now how sweet is that? We have pi on 3, this bit here in the brackets, that bit is the same as u, 1 plus x cubed, that's what u is equal to. So this is u, 3x squared dx, 3x squared dx is du, and now the limits of integration with respect to u, when x was 0, u was 1, when x was 2, u was 9, and that is probably one of the simplest integrations that you'll ever have to do. It probably is. That'll be pi on 3 outside of u squared on 2 with the limits of 1 to 9. Sorry that I've run out of space here a little bit. So we'll have pi on 3 outside of 81 minus 1 on 2, which in the end will give us 40 pi on 3? Have I done that right? 9, yeah, 9, 2, 8, 9, yep, 9, 81 minus 1 is 80, 80 on 2 is 40, 40 pi on 3. So the answer is 40 pi on 3. Okay, a really, really powerful tool this one is. It's a really, really powerful tool, but it's also a complex process to get your mind around at first. But once you've got your mind around it, it's just a pattern. You just follow the same pathway round and round and round, and it's not that complex. It is initially, but it's not once you've practiced it. So again, I'll leave that one with you. Work through the worked examples, keep looking over the video and the explanations. Hopefully that is a helpful tool. And then keep practicing the problems in the textbook. All right. Have good holidays.